Okay, good morning. We're going to talk about revising the atomic model. And so you all have learned about Rutherford, and now we're going to talk about Bohr. And if you had Miss Rush, I know that you went over the Bohr model. I'm assuming that Miss Wiggins did as well. And so what did Bohr propose? Well, he had to expand on Rutherford's model because it didn't explain a few properties and a few ideas that were happening. So one instance is if you were to heat up iron very hot, it glows a red and then an orange color and then yellow. And this was not explained by Rutherford's model. So in 1913, you don't need to know that date, but Niels Bohr proposed a revision to developed a new model for the atom, and he incorporated some newer discoveries on how the atom changes when it absorbs or emits light. That's the important part. It was all about light. So he proposed that an electron is found only in circular paths or orbits around the nucleus. Each possible orbit in a Bohr model had a fixed energy, and these are called energies, and we still use this idea. A quantum of energy is the amount of energy required to move an electron from one energy level to another, and we still use that idea as well. So the Bohr model is kind of like looking at the atom as a ladder, and that there are specific energy levels, and you could only step on the rungs of the ladder. So it could only be at one rung or another. It couldn't be hanging out somewhere in between. It also shows that they're unequally spaced, that those rungs get closer together the further up you go on the ladder. And so the higher energy levels are closer together. How does the Bohr model improve on the Rutherford model? And you should definitely know this. It says it's a checkpoint. The Rutherford model could not explain why elements, when heated to higher and higher temperatures, give off colors of light. It explained how the energy levels of electrons in an atom change when the atom emits light. What does the quantum mechanical model determine? So now here's the third model. We've talked about Rutherford, Bohr, now we're doing the quantum mechanical model, and this is the one we actually use in chemistry today. Schrödinger is the theoretical scientist who proposed this model, and he had to write a mathematical equation, and the solutions to that tell us certain things about the atom. The modern description of electrons and atoms, the quantum mechanical model, came from the mathematical solutions to the Schrödinger equation. Like the Bohr model, the quantum mechanical model restricts energy of electrons to certain values. Unlike the Bohr model, however, the quantum mechanical model does not, I repeat, does not specify an exact path or an orbit that the electrons would take around the nucleus. The Schrödinger model or quantum mechanical model is all about probabilities. Quantum mechanical model determines the allowed energies of an electron and how likely or what is the probability of finding an electron in various locations around the nucleus. Probability describes how likely it is to find an electron around the nucleus. So here we have a probability or solution to a Schrödinger model, and that light bluish grayish color you see on the screen is the electron cloud, and where it is darker, the probability of finding an electron is higher. And so it's all about probabilities. How are the quantum mechanical model and the Bohr model alike, and how are they different? Well, the Bohr model and the quantum mechanical model restrict the energy of electrons to certain values. However, the Bohr model had a specified path. The quantum mechanical model is talking about probabilities, and it is not an exact path. So how do sublevels and principal energy levels differ? So we've talked about energy levels. Now we're going to talk about sublevels. Solution to the Schrödinger equation gives you energies or energy levels of an electron. Each energy level in the Schrödinger equation leads to a mathematical expression called an atomic orbital. Not an orbit, but an orbital. An atomic orbital is represented pictorially by a region of space where we can have a high probability of finding an electron. The energy level of electrons in the quantum mechanical model, the principal quantum number, or the first quantum number we talk about, is n. And n is designated with integers starting at 1, going up to 7 if you're describing just the periodic table. But they actually go on to infinity. Each principal energy level greater than 1 can have sublevels. These energy levels with a principal energy level constitute energy sublevels. So each energy sublevel corresponds to one or more orbitals of different shapes. The orbitals describe where an electron is likely to be found. The two shapes you need to know are going to be for S and P. So the S orbitals are spherical, as you see in the yellow on the left, and the P orbitals are dumbbell-shaped. This is one of the 3 P orbitals. So when we go to this slide, we see that there are ones on this is the x-axis, this is the y-axis, and this is the z-axis. They're in 3-dimensional shape. The d orbitals are getting quite complex, and we'll talk a little bit more about that. But you should know that for energy level equal to 1, there is only one orbital, and it is an s orbital. When we have p orbitals, we can only have 3. When we have d orbitals, we can only have 5. And when we have f orbitals, we can have 7. These are the d orbitals again. When we have 4 of the 5 d orbitals, they look very similar to the p orbitals, but now they're in between, like the x and the y and the z axis. And the fifth one is really kind of bizarre. It's an interesting shape. So I suggest you pause this video here. I do expect to see this in your notes, because when n equals 1, we have one sublevel, and that's 1s. And we can put 2 electrons into an s orbital. When we have n equal to 2, now we have 2 sublevels. So the number for the energy level and the sublevels is always the same. And so the types of sublevels we have when n equals 2 are s and p. And we can have 1 orbital and 3 orbitals of those types. So that's a total of 4 orbitals, which would give us 8 electrons, because we can put 2 electrons in each orbital. And when we have n equal to 3, we have 3 orbitals. Now we've added the d. D can have 10 electrons, so 8 plus 10 is 18. And when n equals 4, we add the f. There's 7 f orbitals, which is 14 electrons. So 14 plus 18 is 32. Principal quantum number n always is equal to the number of sublevels, and the number of orbitals in the principal. The number of orbitals in a principal energy level is equal to n squared. So if you want to know the number of orbitals, you square it. The maximum number of 2 electrons can occupy any orbital. So if you want to find the number of electrons, it would be 2n squared. And you would square n and then multiply it by 2. So if we want to do n equal to 5, we're going to square 5, which is 25 times 2 would be 50. Why do scientists no longer use physical models to describe the motion of electrons? Well, previous models were using classical mechanics, motion of large objects, and they just don't apply to very small particles like electrons. So we had to use theoretical calculations to find probabilities of where we can find an electron. Oh, we're at the key concepts. So Bohr proposed an electron is found only in specific circular paths called orbits. around the nucleus. Quantum mechanical model now gives energies that are in probability or regions of space around the nucleus, and these are now called orbitals, and they have different shapes. You are expected to know the shape for the s and the p orbitals. Vocabulary: you should know energy level, quantum mechanical model, atomic orbital. The big idea should also have in your notes: quantum mechanical model of the atom comes from solutions to the Schrödinger equation. Solutions to the Schrödinger equation give us the energies of an electron and can have in these atomic orbitals, which describe the regions of space where an electron may be found. And that's the end of this section. I look forward to seeing you in class. Have a great day.